All right. I have to change the recording to Zoom because it comes with the transcript, okay? But anyways, it is for the ADAS stuff. Um, all right, so we are gonna get into this chapter 3, kinematics of a rigid body. Of course, I've already um one moment. I'm trying to understand how to do this a little bit. Um, okay, this is okay. Let me practice a little bit how to control this thing because sometimes it's not doing it. Maybe I think click here. Okay, I think I kind of get it. We have to click on this thing before we. All right, sorry about that. Okay, so we're gonna get into chapter 3. So kinematics of a rigid body. Um, so okay, so today we're gonna get into rigid bodies. So moving away from particles. We have already studied, particles, objects in the bodies. Everything we have living or non-living, we put them into these categories before we ever start to break down the motion to study, okay? Um, and in this chapter, we're gonna study a little bit bigger stuff, and that's we call it rigid body. Real machines, of course, in mechanics and mechanical engineering or mechanical engineering technology, um, we don't have points. So instead of points, you have to look at them like your wheels, gears, your fans, your robot arms and tools, etc., etc. and etc. So, but you can relate points, objects, rigid body to everything we have in mechanical engineering technology. Even though they, like try to put the name mechanical technology, something like that, the curriculum people. But that just like trying to coin a different name, not to call, not to overlap with other department, but is actually is mechanical engineering technology. We don't have mechanical technology, okay? So anyway, it kind of sound weird, but the principle is the field is mechanical engineering technology. We're trying to propose to change it back, and the leadership is not. Uh, I don't know. We still need to work on that because it just making like student understand in a very different way. Of course. Um. Okay, so because some students think like, MT is not equal to MET, but actually it's equal. Yeah, totally. Where we are that. And it's just the way that they define it is just making people very confused. But we're trying to fix it, and probably, we will succeed to change the name back to where it's supposed to be. So anyway, let's go back to chapter 3. So this lesson is going to explain how the rigid bodies move, okay? And we're going to use a rotation and of course translation without going into the heavy calculus. Dynamics cannot be taught, okay, without calculus. We can like simplify it into algebra, right? Simple ways to calculate mathematically. However, dynamics is calculus. It will be very difficult to do it without calculus. So you still need to understand like how we use calculus to be able to understand motions. So calculus is two ways. The one is you break down into pieces and study piece by piece. The other one, of course, when we study the change, right? and piece by piece we name it mathematically differentiation. And the other one is going backwards, and that is integration. Integration is we bring all that little pieces all together and make it, accumulate these little pieces all together so you get back the entire system, kind of like that. So it's like going from components to system integration, system to little components, and break it down all the way down to the very, like small changes that we try to look at it. And of course, that we call that differentiation. Yeah, and you're going back and forth between that too. And of course, you have to study many different levels. Yeah. And don't forget the space. Calculus 3 is nothing about the space. Yeah. Anyway, so let's get back to here to kinematics. Okay, we're not going into causes of the motion, we're just studying the motion, yeah, itself. Of course, when we combine rotation and translation together and we study the motion, okay, in rotation and motion and translation like that together, we call that general planar motion. In fact, it was quite like general plane motion, plane, okay, on the surface, kind of like that. But then later on, people write a general planar motion, something like that. Yeah, but it is the same thing. Okay, so you should know that when we talk about the kinematics of a rigid body, right, by now we're moving beyond particles and we're moving into real mechanical systems. Okay, so up to now we have treated our objects like points, of course, the particles with no size. And well, that works for basic motion, but real machines, are not points. Okay, so if you understand that, that would be the first thing you have to understand in mechanical, engineering technology, of course. Um, So real systems are, I have already, told you, and I also write a little note for you to remember. So the wheels, gears, of course, the fans, robot arms, and tools. So these objects have like shape, okay, and then don't forget size. And of course, they can also rotate. And that changes how we analyze the motion, okay? Rotation, um, just change the way we think about or analyze the motion because we've been studying like straight line, like curved line, like that. So this chapter is again is going to focus on this kinematics of a rigid body, and you really, really need to understand what kinematics is. Okay, so that means that we're studying how these rigid, objects move and not why they move. So we're not using forces yet, just the motion. Okay, we're going to concentrate just the motion. So especially we're going to study the general planar motion in this lesson. And I already explained what the general planar motion is, just a few minutes ago, but I'm going to repeat it again so you kind of get it. So this means like motion, that happens in a surface or a plane, okay, where one object can translate and then rotate at the same time. Okay, so it's really, really important that you know they translate, the objects translate and rotate at the same time. So a classic example is like let me think. Like a wheel, rolling on a, let's say, on a ground. So the center of the wheel moves, okay, forward when the wheel is rotates. Okay, so you gotta understand it is moving forward and then it is rotating. Sometimes you think like the wheel is going just, rotating, rolling, you would say, but rolling is rotating and going forward. So don't forget that, to be able to truly understand what dynamics is. So that combination of moving forward, translation, and then of course rotation, is what we call general planar motion. Yeah. I already said a long time ago, they say general plane motion because it is, motion that we deal with a plane. Okay, that happens on a plane, I would say. So by the end of this lesson, you're going to be able to recognize different types of rigid body motion and then, of course, describe them using velocity, and of course acceleration. And we're trying to make it, not to use a calculus, especially for this course. Yeah, so that way, the student can be able to follow. And again, dynamics itself is actually calculus, and we can really get rid of it. We can simplify like what we're doing right now for you to be able to understand. But as you study from the one level to another, you really, really need to go into calculus one, two, and three. There is no way out. And my department chair told me to reinforce mathematics, so that comes from the state. So we will be supplying math book one, two, and three for you. So that way, when you bridge from this college to the university, you won't have any kind of issue, okay? If you don't need it, then you can ditch it, of course. It depends on what you want to do in your life. All right, of course, we will go into the learning objects because we need to also write this down. So before we get into the details, yeah, we gonna look at the big picture of what we're gonna study. So of course, first you should be able to explain the difference between translation, rotation, and of course your general planar motion. It means that you can look at, let's say, an object and then describe how it's moving and just say, that it is moving without thinking what caused them. And of course, second, you should be able to identify um I would call it like annual motion quantities, yeah, especially for your angular displacement, angular velocity, and of course angular acceleration. You need to know that three things. These are the rotational versions of position, velocity, and acceleration that you already know from your linear motion. Okay, chapter 2. And then, of course, you should be able to relate angular motion to the linear motion. Angular and linear are two different things. And that is a key skill that you need to improve, okay, or learn. So we're going to connect rotation to straight line motion using simple relationships, like how the speed of a rolling wheel relates to how fast it is spinning, okay? And then, of course, finally, we're gonna solve this basic rotation and rolling, okay, problems. So these problems will focus on understanding the motion, and of course, not your heavy math. Okay, math is just we use it for for I would say like math is just a language. Okay, we use it to describe what we want to say, and we can do it by using a regular language. Okay, it's got to be math because math can be able to bring a lot of the uh, description and explanation into very compact equation. Okay, so it's kind of like a decoding what's been coded by using the math language. Okay, so I usually say math as a code, not as a language. Of course, many, like way before us, use it like a language. So there is a looseness in how we define things. But for math, I just see it as we code something and we're gonna decode. What somebody put all together and about something that somebody want to say. Yeah, anyway, so it's actually to me it's like that. Yeah, so I'm always interested when I read an equation. I want to know what that is about. Of course, many students here at the college, community college, they always afraid of the heavy math, and you don't need calculus again for this lesson. Everything builds directly on the concept you have, know so far from the chapter 2 linear motion, and of course, so we're gonna apply that to rotation and rolling, objects. All right, then why rigid body kinematics matters. So let's talk about why rigid body kinematics is very important for us to study in engineering and engineering technology. Of course, our background is all engineering. So in the real world, machines are not points. Okay, I already told you that on the very first slide, and they are we call them rigid bodies, yeah, because they have size and of course they have shape. You know, you have size and you have shape. I have my own size and my shape. They are different, yeah. And if you look at many objects all around us, they have their own size and shapes, yeah. So when something moves, of course, let's go back to real world, let's say in industry, it usually moves as a solid object, you know, and we start to call it rigid body, solid object, solid modeling. Okay, so try to recognize the terms that we use in engineering and manufacturing field. That's where you really are. Okay, so not as a single dot line in physics. Yeah, so the physics and mechanical. The physics dynamics and mechanical dynamics are very different because physics usually do it with a lifeless dot, okay, and of course a little circular objects like that, but we do it with real machines, yeah, outside solid. We call it the solid objects, machines, devices to so and so. Yeah. So components in machines, they can translate. So if you think about the machine that is a system and every system has components, okay, just like we are systems and our body can go all the way down to very little tiny particles, just like that machine also has it. It's just rigid, you know, they're not soft. So anyways, a machine is a system. It composed of components, you know, units. Of course, they have it is an assembly, okay, and it has many sub-assembly. It depends on what machine that is. Always sub-assembly, complete assembly, and then sub-assembly, and then of course components in these assemblies. So these components in machine, they can translate. Yeah, it means like they can move in a straight line. So they can also rotate, meaning they spin about an axis. You know, every time you think about rotation, it's kind of like imagining a circle, and the circle has a little center. Yeah, and we talked this center like an axis. Okay, so if you think about a body, okay, it's not a circle anymore. It become like a circle, a rotating thing. Yeah, and we see it's like it is, you know, spinning about an axis. Okay. So and very, very often they do like both at the same time. Like they translate and of course they rotate at the same time. Yeah, it is really important. So think about the wheels, the gears, the fans, the pulleys, and robotic arms. All of these systems, they involve rigid bodies undergoing rotation, translation, or a combination, okay, of both. So that's what we're talking about here. Yeah, components rotate, translate, or do both of them. Of course, listing like this is simplifying all this, you know, like explanation, yeah, into a very rigid way of outlining. So anyway, so your rigid body kinematics gives us the tools, okay, the tools to describe that motion very clearly and also very correctly. So it's kind of like a foundation for us, yeah, foundation to understand how our machines move before we ever talked about forces, before we ever talked about power or stress. Okay, so this topic is going to give you the stage for later topics in kinetics and of course your machine analysis. So if you understand how motion works here, everything, okay, everything that follows is going to become much easier, yeah, for you. All right, then we are going to get into this types of rigid body motion. Okay, so before we calculate anything in this chapter in rigid body kinematics, we need to start by classifying the type of motion. You know, you have to know. So we have like a rigid body can move in three different, you know, we make it three different categories, so they can move in three different ways. And every problem we solve, of course, on the paper or in a computer, are gonna fall into one of these categories. Yeah. So the very first one is your pure translation. Of course, in pure translation, you gotta think and know that every point on the body, yeah, is gonna move in the same direction, and then of course the same distance. And the object does not rotate. Okay, so now we get a little bit more details into this pure translation. So they're gonna move in the same direction, and then of course same distance. And of course, the object is not going to rotate. Okay, so that's translation. No rotation in it. Um, let's think about an example to give you. So an example of a pure translation would be something that you know every day, your elevator, yeah, moving straight up, or a box, right? A box is sliding across the table without tipping or without spinning. Okay, that's a kind of a translation, a type of rigid body motion. Now, another type is called pure rotation. So in pure rotation, your body rotates. And every time we think about the rotation, we think about there is a center and there is, of course, fixed axis. Okay. So different points on the object move different distance. Again, I said different points on the object move different distances because the object is a solid body. And again, you gotta go the levels of stuff, in every object. We see the object as a composition of components. So every object has it's breakdown able components, and we call them, and we try to simplify by looking at the object is composed of a little tiny, a point or a drop of material. That's how we imagine or understand the object. So when you think about the object has so many, object is made of material, material from your periodic table, from hydrogen all the way to, it's got a composed of something, some chemical elements. And of course, we break it down into each little tiny particle, and we call them just a dot when we study it. So, and when we say, this object, we have to understand that we're breaking down into tiny little points on that object. So each point again is moving. So relative motion is not just two different things moving. That's too big. You gotta understand, like matrix, you gotta understand and go straight into many pieces that make up the object. So you know that there are many little tiny things in the object, and each one of them is moving. Yes. And of course, we pick the reference point, and that reference point is your axis. So different points on the object move different distances, again, away from that axis, okay? Sometimes towards the axis, depends on how the motion is. Okay, so right now, just understand the references, the fixed axis, and we are gauging, away from that axis. And of course, measuring how far away from a point in the object is from the axis. So this is how we study the motion. Motion is studied by components and the system. Okay, every time the system move, we are aware of all the stuff inside of that system at different level, different sizes. Okay, and different position they move with it. Okay, so that's the gist of dynamics. Of course, they all rotate together. So they move together, they take the distance together, and they rotate together. In this case, rotation, pure rotation. Okay, and that's a very, very important point that you need to know, and never ever look at the object as object anymore. You have to look at the object and then the internal composition of that object, and we make it simple by saying points. A gazillion of points in every object, by the way, just like there are a gazillion of cells in our body. And again, each cell has a gazillion of stuff inside as well. So the world in the worlds. So that is our world. Our world is going into. That's why we think about where we actually located. Are we in the belly of the gods or some stuff like that written, in different books? Coming from this kind of idea, the world in the worlds, many, many different levels of world. Life is going on non-living things are also going on composed that way, as far as what we know until now. Okay, then I'll have to give you the example. Yes, a real world example. Let me think about the routine. It's gonna be your ceiling fan. Yeah. So if you think about your ceiling fan, it's spinning about its center. So you can see the center of the fan. You can see the center, the fan blades like that. Or you can also think another example would be door rotating about its hinge. Yeah, that's a pure rotation. There are the examples of pure rotation. Then we're going to get to the last one, which is a general plane of motion. So general plane motion is also called general planar motion, and we also call it general plane motion. It's the same thing. It happens on a plane. So this is the most common type of motion in the real machines, in real world, in mechanical engineering and engineering technology, of course. So in general plane motion, the object is going to translate and rotate at the same time. Don't forget at the same time, all right, phrase. So a rolling wheel is the classical example of a real world example. The wheel rolling. So the center of the wheel gonna moves forward while the wheel also rotates about its center. It is very different from elevator move up and down. It is very different from your fan, okay, rotating at an axis, okay, stuck to the ceiling. And try to understand the differences between the motion of the fan and the motion of a rolling wheel is very different. Rolling wheel has a translation and rotation together. Your ceiling fan has only rotation, okay, and your elevator has only translation. Yeah. So now we try to break down motion and then put them into three categories, at this lesson. So engineers, we like to identify the type of motions. That's the very first thing we do in our head. Okay, every time you analyze what happened to this machine, that machine, we try to see, okay, what could have happened? Yeah. So every issue comes from some sort of motion. So the first thing we do in quality, of course, the quality assurance, the quality system, we're studying a lot of the processes, what could have gone wrong in these processes, who did what, okay, track all the way to the root, of course, cause of the problem. So the first thing you do is you identify the type of the motion. So, and then of course, because each motion type is going to use a different relationships and of course a different equations. Okay. Um, so that's the reason why the types of rigid body motion is extremely important. So if you classify the motion correctly, the rest of the problem becomes much easier to handle. Yeah. Of course, and people don't understand. They always think like engineers, okay, people who have to use a brain, like don't do any kind of work, things like that. But actually, you're doing the brain work. The brain work is as stressful as a physical work, okay, because we have to think. We have to think and understand how something happened. Yeah. So if you do only the physical stuff, then your body worn out and your brain won't think. At that time, of course, the technicians and the engineers gotta work together. The engineers use incredible amount of brain to sit down and think about the situation so that you won't get issue. So when we do manufacturing, we're expecting these machines to run 24 by 7 reliably. Okay, so your reliability gotta be between 80 to 90. I would say like 96%. 4%, 5%. There is error default, of course, the system error is always there to play around. So we have to work together, So the engineers and the technician don't should not hate each other, And of course, in a country, incredible amount of issue happening between the two big groups, So technicians think like they should be paid, okay, more than the engineers because they have to do the physical work the engineer don't do, but a lot of the methods are formed by the engineers, and without them, without their thinking, you can't be able to have the machine that runs, all the time. You know how to fix a machine, but we know how to sustain that machine, from and be able to run it for years. Like I always give you example of your car. Your car, you have 1 year, 2 years, stay 20 years. You go there, if you do a regular maintenance, it will definitely go, okay? And you turn on your car key or press, like press the stop button, it's gonna go. So your machine is reliable because like people who design that, people who design that, people who build that, they think 360 degrees around what can happen and how we're gonna prevent that. And it starts from these three types of rigid body motion. Okay. All right, then we will go into pure translation in detail. So let's start from the first type of the rigid body, and we call that pure translation. Yeah. So here in this motion type, all points on the rigid body. Again, try to see every body has so many points. Okay, we're just making points. So every time we say points, material-wise, that's a little tiny, okay, component of the rigid body. It has some material. That's why you can be able to represent that little tiny material as a point. Okay, we can call it so many particle composed of that rigid body, and then we're going to see a point to point. Why do we do point? Because we can put that point in the coordinate axis, your X, Y, Z, yeah, your 3D axis. So that way we can be able to measure whatever we want to measure and calculate, yeah. Okay, so all points on the rigid body move the same distance. Yeah. And of course, they're gonna move in the same direction. So all the points that make up the rigid body are going to move the same distance and in the same direction. Yeah. And of course, so that means every point on that object has the same velocity. So we're taking some distance over some time. So therefore, since they're taking the same distance, they are going to have the same velocity because we're looking at that distance over the same time. Okay. So, and of course, because you have the same velocity, you're going to have the same acceleration as well because we're looking at the velocity with another timeline, yeah, over another timeline. So therefore, you have the same acceleration. So the key idea here is, that look at this, how this is moving, okay? So the key idea, like here is that no rotation happens. So that's the first thing you have to know in translation. Okay, no rotation, of course, happen. Yeah, look at this. Yeah, I just activate this so you can be able to see how translation. There's no rotation is going on in the block slide. Yeah, just like down in one direction, and everything, of course, make of that block. See we see all the points, inside of that little tiny block. They're gonna also move in the same, direction and in the same distance, of course. So again, the key idea here is there's no rotation, no rotation in pure translation. And of course, the orientation of that object does not change as it moves. Yeah, orientation is going to be the same. So if the object does not spin, it does not tilt, it does not rotate, then the motion is pure, okay, translation. Remember that forever. So the image on the left, okay, so this one, carefully look at it again. So it's going to show a block sliding as one solid piece, even though it is moving and the block does not rotate. It simply shifts the position, and so did all the points in the block, okay? So a simple engineering example, let me think what to give you again. Your pure translation is like a toolbox, like sliding across the floor, okay? Just like this block, like slide. Here's your landslide right there. So, and of course, every corner of that toolbox is going to move together. So that all the points in that toolbox will move together. Yeah, so the toolbox is going to keep the same orientation the entire time of that motion. Okay, so whenever you see a motion where the object slides without spinning, you should immediately classify that motion as a pure translation. Okay. All right, the next one, we will get into the second type, which is your pure rotation. So now let's look at this type, this type of rigid body motion. So in this type, of motion, we call it pure rotation. Your rigid body actually rotate about a fixed axis. Okay, so I show you the little center right here. Look at that. Okay, this is your rigid body. Of course, we take a look at, okay, from that point, your eye is here and looking at this, and of course, we cut it out and draw it. And you can be able to see the center point right there. Yeah, and that is your axis line. Okay, so this is your body is rotating about, okay, a fixed axis. So the axis doesn't move. That one stay totally, okay, without movement, by the way. The only point that doesn't have any kind of movement is there, okay? It is right there. Of course, in a very, very hard, okay, quizzes or tests, we encounter something like that. Like all of the points in the rigid body, okay, moving or rotating in a pure rotation, you say not all the point is because the point at the axis does not move. Okay, so therefore that's kind of a tricky question. It usually tricks the student. So anyway, so the axis does not move and the body spins around. Okay, your body spins around, but the rotation is happening at a fixed axis, and that point doesn't move along that line. Okay, so I always say the entire line. As you know, a line is composed of many points, and we call it, a series of points, dots are called line. So now, every point on that body moves in a circular path centered on that axis. So now we're going to take it out, take it out from this rigid body and draw a little circle to be able to see how points are moving in a circular path. Okay, so you can see this, of course, a diagram like this. So every point on that body moves, okay, in a circular path. Don't think like only there's a one circular path. No, it has a gazillion of circular path from there all the way to, okay, to there, except that central line. Okay, so your body has a material field from here all the way to the end of the circumference. Okay, and each one of them is a point. So if you say like calculus, yes, it is very complicated. Yeah, and we only take one point out in calculating, and even that is hard for you. Yeah, so that's why we can do it with human brain. We have to use computer, very, very heavy computations got to be only done by the software. So anyway, so every point on the body moves in a circular path centered on the axis. Very hard tests in different university, of course. Don't show only one circular path. You have like one, two, three, all the way down. Yeah. So if I draw a little circle, different size, and you freak out, you don't freak out. That's a part of that rot anyway. Yeah. Okay, so a very important idea here is that all points on the body share the same angular velocity. Yeah, so now we think about the velocity because we know the distance, how it is moving in rotation. So now we think about the velocity. Of course, in a straight line, we call that just a regular velocity. But for rotating, like things like this, we're gonna call it an angular velocity. Yeah, it's just a velocity, but velocity going in a rotation, and we call that the velocity of the object in a rotation, okay, motion. We call that the angular velocity, and we use a little omega. Yeah, so here there is a little omega right there. See, another symbol, a very new symbol for you, and that is your angular velocity. So every time you see this little W-like symbol, that is your angular velocity, and you are dealing with the rotation. Okay, you're dealing with the rotational velocity. So even though angular velocity is the same everywhere in that rigid body, in rotation, the linear speed is not the same for every point in the same body. Yeah, so we have two different velocity. One is the angular velocity, and the other one is the linear. Okay, linear velocity. We also call that the linear speed without the direction. Okay, if we put the direction on every point in the object, we call that the linear velocity. Yeah, don't forget every speed you can add the direction. When you add the direction, it becomes a velocity. Yeah, points that are faster from the center of rotation are gonna move faster in a straight line sense. Yeah, than points closer to the center. So there are many points, of course. So the points that are closer to the center, okay, and the points closer to outside. So fast, you gotta understand like the points that are farther away, okay, from the center. So around here, yeah, your rotation, the center rotation is here. So all the points on this side is gonna move faster, yeah, in a straight line. Um, so we're just thinking like, what if they move in a straight line? They're gonna move faster. And of course, we draw the straight line like a tangential line like that. You know, if you straighten this thing out, it's gonna be like a little tangent, you know, attached to the circumference. So faster in a straight line sense, the point's closer to the center. So the object shares again the same angular motion, yeah, but the linear speed is going to depend on how far away that point is from the axis of rotation. Nearer is going to be slower, and of course, further away from that axis to the outside, linear speed is going to be faster. Linear, not angular, okay? Angular is going to be the same. You have two different, again, velocities going on. One is a linear because we draw a tangential line, and there can be a tangential line. Every time there is a tangent line, it is, we believe that it is going in a straight line. Yeah, even though we draw the tangent line right across there, one point is, like is sharing the circular path, and then of course a tangential path. Yeah. So I want my pen here so I can be able to draw like that. So we see like this, okay, a straight line. So this point, okay, and we measure like a linear, of course, is speed. And then of course your angular, okay, speed it is here, yeah, happening. So slower here and then faster here for linear speed. Okay. Angular speed is going to be, this one is going to be pretty the same. Yeah. Okay. Um, so the classic example of this type of pure rotation motion is like, let's see, a disc. Okay, so you have a disc and then it's going to spin about its center. So when a disc is spinning about the center, okay, you're going to get pure rotation. Yeah, or again, I already gave you the ceiling fan. Yeah, so the fan blade rotating about its shape. So the tip of the blade has a greater, okay, linear speed than the end of the blade, which is closer to the center. But when you think about the angular speed, it would be the same. Yeah. So that's all you need to know about pure rotation. All right. Now we are on the general plane of motion. Again, it has two names, general planar motion and also known as general plane motion. So, and this is the most important type of rigid body motion. Yeah, I already told you that. Because this motion, you have translation and then you have rotation. And both types of motion, translation and rotation, are happening at the same time. Okay, that's what you need to understand. So this is the most common type of motion in real world mechanical system. Okay, why this general plane motion is so important for us? Because it is the most common type of motion in the real world mechanical systems, any one of it, by the way. So very few objects only translate or only rotate in our world. Most of them, they do both at the same time. Okay. So if you get that much, I'm going to be very happy. So this motion, okay, this type of motion happens when your body moves forward. Also at the same time, it is spinning. Okay. So a rolling wheel, already gave you that example in previous slides. Rolling wheel is a classic example of a general plane motion. So as the wheel rolls, the center of the wheel translates forward, while the wheel itself rotate, okay, about its center. Yeah. So if the wheel rolls without slipping, it is doing two things. Okay. If this wheel is rolling without slipping, it's doing two things. Okay, at once, of course, moving forward and then rotating. So that combination is what defines general plane, okay, motion. So the motion happens entirely in a plane, which is why we call it general plane motion. Yeah. And of course, throughout this chapter that we are learning, we are going to analyze the general plane motion by separating that, okay, separating it into translation, yeah, of a reference point. We cannot measure without a reference point, so you always have a measure, okay, measurement, a reference point. And of course, usually the center and the rotation above that point. Yeah, because since rotation is also happening, we usually use the center as a reference point to measure everything. Yeah. Again, what are we measuring? You're measuring each point. Yeah. And comparing each point, which one is going faster and which one is not going faster, what's going on with the, okay, angular velocity and what is going on with the regular, okay, velocity, which is your linear speed. So once you get that, once you get both motions are happening at the same time, when you get this, all right, general plane motion, then the analysis, okay, become very, very manageable. Yeah, as long as you don't get this, they're happening at the same time, how they move forward and rotate at the same time, and can be able to break down into pieces, different points, a different location, again, with reference to the center. That the center point is your reference. That's why we always put a zero right there. So every time the zero, it means we're measuring from here to somewhere. Yeah. It can go beyond this line, by the way, but always remember that there are many circular paths, right? Now, if I draw a little circular path and don't say that that's not my rigid body, that is your rigid body. We just concentrating in that little circle instead of that. Yeah. I got my PhD because I can be able to see these things, okay, very clearly. Even though my professor always say I can fool her because we get it anyway. Yeah, because you have to read it very carefully and also remember and get what it is saying. It is saying the circular path. It never say there's only one, yeah, circular path. It says circular paths, and according to the points away from that reference point center. So you have gazillion of circular path, okay, projecting from this center all the way to the end of this, but it cannot go anything more than that distance from here to here. But of course, you can play gazillion of points, from here all the way to here, 360-degree around on three different axes in your 3D space. Okay. So if you get that, you can be able to solve the problem very, very easily. Yeah. All right. All right. So what do we have here? Angular quantities. All right. So angular quantities is like, all right. So oh, one minute. Okay, so now we introduce a basic angular, all right, quantity. So we get into angular quantities. Of course, don't forget we are in the limited to the rigid body rotation, okay? So rigid body rotation, we use three angular variables. Yeah, quantities now we call them variable. It's the same thing because they vary in their value. It can be anything. Yeah, so they, of course, they directly mirror the linear motion. Quantities you already know. Yeah, so what it meant is like even though we write it this way, angular displacement, and then of course they give you a little symbol, right? Theta. Of course, we measure in radians is a first angular quantity, the first variable. So the first is the angular displacement. And of course, this little symbol, yeah, if you're not familiar with the symbol, so that's is called, its name is theta, yeah. So angular displacement measures so how far an object has rotated, yeah. So we call that the displacement. Since it is rotating, we put the name angular so you don't confuse with your linear, yeah, displacement. So angular displacement, every time we say angular displacement, your object is in rotation, okay? And we, of course, start to use theta instead of x, yeah? So, of course, you measure, yeah, measure and your radians is your unit, yeah? So that's not degree. Radians are different, but it's just another unit type. Of course, the second quantity, angular quantity, is called angular velocity. If you have a displacement, you got the velocity. If you look at that displacement over a period of time. And of course, we give a little w, which is your omega. Yeah. So of course, omega is your Greek, little symbol, W, little w like that. And of course, since we're looking at the radian, the displacement over a period of time, your unit is rad, okay, divided by s for the time. And the last angular quantity or variable is your angular acceleration. So when you get to the angular, right, the third quantity, angular acceleration, we're gonna represent that by using another Greek letter, and it's called offer. Yeah, so this is your offer. It looks like a letter A, of course. So angular acceleration is going to tell you how we're looking at the angular velocity changes, yeah, with another timeline, which is your time. See, we have two different timelines. So every time we have two different timelines, their quantities, okay, their quantity grow in exponent. So that's why we have a power two right there. Yeah, it means like power two means we have two different timelines. And of course, we're looking at the distance. You know, what happened to the distance that this rigid body, all right, takes in that motion. Yeah, we're measuring. We have to measure, otherwise you wouldn't have any kind of motion. Yeah, we wouldn't know where to go from where to where. Okay, so the key point here to remember is okay, this structure, of course, is exactly the same as your linear motion. You have your distance, you have distance over time velocity, and you have velocity, change in velocity over another time is your acceleration. Okay, another amount of time. I hope you get it. Okay, the same structure, but just different variables name and different units name. Okay, and different symbols, of course. All right, so the next one we're gonna get into angular velocity. So here let's focus on this. All right, velocity is very important. Now we know that every time we think about the velocity, we're thinking about the distance and we're looking at the distance change in distance over a period of time. Okay, starting from here and ending over there, and what happened to my object? Yeah, in this case, in this chapter is your rigid body. It moves from here to here, and that okay amount or that much of distance. Yeah, so you're looking at that. So that is your velocity. And then now you're going to apply the same concept to the rotation. Yeah, so in your rotation, you have angular velocity because you're looking at how fast that rigid body, okay, rotates. When you think about the rigid body, again, you're not thinking about the rigid body as a whole. You think about the rigid body as a whole and a little tiny pieces. And we define little tiny, the pieces as a down to the very smallest material, and we call that a point. Yeah. So your points in the object and the object rotates at the same time. So it tells you how quickly that angular position changes with time. Angular position belongs to every point, right, in the object and the object itself. Okay, so we of course we talk about this angular velocity, yeah, with this a little symbol, of course, we call the omega is its name, and it looks like a little it looks like a little W, okay? And okay, your distance is gonna be, yeah, angular distance is gonna be theta in radians, and then of course yeah, T, because your rotation is like a circle, you know, when you draw it in 2D. So therefore we go with the little theta, and then of course T, yeah. So mathematically, angular velocity is defined as your technical term is angular displacement divided by time, okay? We call the distance displacement is because we are looking at the distance with the direction. You know, where is it going? Okay, so it means that we're measuring how many radians an object rotates, all right, per second, the objects and the points inside of the object. So don't forget the points inside of the object. So one important idea is, is that every point on a rigid body has the same angular velocity. Tell you again and again, you have two different velocity. We're studying two different velocity in every rotating, okay, rigid body. One is a angular velocity. It is very good because it doesn't change, so you don't have to think about so much. It is always constant. And then you have another velocity, and that is we're gauging with the little, okay, tangent, all right, line. And that, of course, is your regular. We call it regular, or you can also call it linear, okay, speed. All right. Of course, if you put the direction, it's going to be linear. Velocity, of course, at the same time. So very important, yeah, thing is that every point on a rigid body has the same angular velocity. Don't forget that. So even though, all right, even though uh different points, they're gonna move at different linear speed, um, but they all rotate, all right, through the same angle in the same amount of time. Yeah. So that the same angle in the same amount of time, which we call this the angular velocity. So every time you see that this is radian and we're dealing with the angles, all right, distance, yeah, distance. So I can draw that for you again. So let me open this draw thingy. Yeah. We're gonna go back to the circle thing. Yeah. So you have this, all right, paths, of course. And here is your center, okay? Even though we draw our angular velocity like that, your path is defined with this, okay? And of course, so that path is defined with this, okay? And of course, that we call the angular displacement because you go, yeah, your body. Of course, if we're looking at the point on this circumference, it's going to be from here to here. It can be from here to here too. Don't forget the circular parts are the paths are many. Okay, in your head, it's going to be like that. You know, which point are we talking about? So right now, usually point is right there. Okay, but the level one is point is always right there because we don't even test you. Of course, level two, three, four is going to be around here, here, and you have no idea where. Yeah. So if you're concentrating here, then of course your circular pair is going to be crossed like that. And of course your linear, your velocity is going to be there. Your angular is constant. Of course, we're looking at that and it is defined by the theta, which is this, and we call that the radians. Yeah, it even looks like a little degree thingy. And of course, it costs you time is from here to here, yeah, to do that motion. So, um, again, even though different points, they may move at different linear speed, they're gonna rotate through the same angle in the same amount of time, through the same angle in the same amount of time, and have the same, okay, having the same angular velocity. So the units of angular velocity again are radians per, okay, second for time. And we usually say like rad per second, rad for radian, yeah, in short. So we use a radians, okay, instead of degrees, because radians can connect directly to the linear motion again later in the chapter. Yeah. Like a general planar, you know that it's moving forward, you know, without that tangent it would be difficult for you to move, because of that tension has some pull, along that line, and that causes a forward movement. Every point that is tangential has a linear motion with linear velocity, and at the same time you have a angular velocity rotating, okay, in the same rigid body. Okay. I hope you get it. You gotta really, really get it. Okay, so we use a radian instead of degrees, and remember that. And that is because the radians can be able to directly relate to that linear motion. Yeah. For now, right now, just think of angular velocity. Okay, is a rotation version of the linear velocity. Then we come to linear velocity, right? Uh, from rotation, a little more details. Let's go into this slide. So now we connect the rotation, all right, back to the linear motion. Um, so for a point located at a distance, okay, let's say R from the axis of rotation, we can draw, okay, let me get my, we can draw it, okay, like that. Um, So let's just get back to like something like this. Okay, draw like that. So you think about a point located a distant, all right, from the axis of rotation. And let's just make an axis of rotation is there, right? And then of course, we're gonna make a point right here, yeah. And we're just gonna call that R like that, yeah. Uh, this is R. It looks a little bit not R. Let me just go ahead and make this a little bit better. This is R. Okay, a little bit difficult to write it. Okay, so that's a distant R, okay? From the axis of rotation. So here is your axis of rotation. Distance is R right here, okay? So the linear velocity of that point is given by V, all right, equals R times your omega. Yeah. So now we think about the linear velocity, which is this guy, okay, right here. And that velocity amount is this guy, all right, times your angular velocity. Okay, so if you think about how much is a linear velocity at that point, and that point is this distance away from the center. Now, do not confuse, okay, with the radians, right? Radians that we talked about. That's just a distance, okay? So radians and R are totally different thing. Okay, your R is distant from here to here. Okay, so V equals R times the omega is your linear, okay, velocity. So linear velocity of what? Linear velocity of that point of this body. Don't say like linear velocity of the rigid body. No, we're going with a little tiny point. Okay, different location. These points define different location of that body. Even though most commonly in most, most of the textbook, the point is right there, on that circumference like that. But that point can be anywhere, and it would take a distance when you measure from the center about that much of distance, or sometimes this much of distance if your R is here, sometimes your R can be there. So then your distance is from here to here like that. Okay, wherever your point is, if you want a linear velocity, all you have to do is angular velocity times that distance and you get it. Okay, so pretty easy to calculate. So that relationship is going to tell us even though the entire body shares the same angular velocity, which is this omega, yeah, the linear speed depends on how far away, the point is from the center. So now this is closer, and that is longer than that. Yeah, so this point has more velocity because this is more. See, like how if this is long, then of course you have a bigger velocity. If this is small, you're going to have a smaller velocity. Is very obviously, understandable, right? All right. Of course, now I'm going to repeat it again. So this relationship is telling you, look at it very carefully. Your linear velocity depends on the distance, okay, of a point away from the center times the angular velocity. Okay, so the more distance you are away from the center, the faster the linear speed or velocity is. Okay, speed and velocity the same. Velocity has just a direction description. That's all. Magnitude the same thing. Yeah. The shorter the distance of the point in the rigid body, meaning closer to the center, is gonna have a smaller, okay? Smaller, you're gonna have a smaller velocity. Okay, so I was looking away, sorry about that. Somebody over there doing something. Okay, so points that are far away from the axis of the rotation is going to move faster. So if somebody starts to say points that are farther away from the axis of the rotation, going to move faster in a straight line, since then the points closer to the center, you got to get this. Yeah, we're talking about the velocity, and we're looking at a point that is a distance away from the center, and then that thing is moving with an angular velocity of omega. Okay, so make sure you get that. So this is why uh, so let's go back to the ceiling fan again. So that's why the tip of a fan blade is gonna move, right, very fast. Now, of course, the ceiling fan is gonna be not a planar, it's gonna be pure, rotation. Um, until the hub, right? Hub meaning near to the center of the fan is gonna barely move. It doesn't move at all. It's just rigid, right? If you look at your fan, ceiling fan very carefully, you can see the axis, the center doesn't move. It's only the blades moving around it. Yeah. And of course, the tip is faster than the root of the blade. So the angular speed, again, your omega, is the same for the entire body. Doesn't matter where the point is in the body, okay? So where the linear speed is going to change with the radius. But for linear speed, depends on where the point is away from the center, is going to change, okay? All right, so make sure you remember the same angular velocity, omega, different radius, little r, and then, of course, different linear speed, your little v, okay? Is connected to each other with this equation. Okay, so formulas are very powerful because it can describe gazillion of things because of the ability of the variables. Yeah, it means that this can be anything, that can be anything, that can be anything on the number line. Okay, that's infinite numbers of stuff that we can create. Yeah. Okay. All right. For that's it for this thing. Now we're going to slowly move into linear acceleration. Yeah, we're in rotation, but we come to understand there are two things going on. One is angular and the other one is linear. Okay. Um, so when you think about a point on a rotating body, again, you have a rotating body. Yeah. So let's draw this again. So you have a little rotating body, and we're now thinking about a point in that body. Yeah. Um, so when this body accelerate, yeah, it gains some form of acceleration. It can be acceleration or deceleration. It can be plus or minus, but we say just acceleration, some form of acceleration happening in this rigid body. So that acceleration has two different parts going on, yeah. So the first part is your linear, which we call it tangential acceleration, okay, and the other one is centripetal acceleration. Yeah, so when you think about the tangential acceleration, that's completely responsible to the changing speed, okay, of that point. Again, we're looking at a point in the, yeah, in the rotating, of course, object right there. And when you think about the tangential acceleration, yeah, we're thinking about the changing of the speed of the point. So if your object is speeding up or slowing down, so that's what acceleration does, either speed up or speed down. Okay, and of course, don't forget this is rotating. Yeah, your motion is a rotation. So when rotation is happening, it can also speed up or down of the rotating object. Yeah, so when that is happening, your tangential acceleration, okay, happens. Yeah, it is inevitable. It will happen as soon as it rotates. And the object has a lot of points in it. We already knew. We want to concentrate a point. We're going to focus at a point. We think about the tangential acceleration, okay? At that tangential acceleration, we are thinking about the changing speed, okay, at that point. All right, so the second acceleration, second part of the acceleration is called centripetal. So you have an acceleration, but that acceleration, we put it into two different parts. Yeah, one is a tangential, and the other one is a centripetal. The second part is a normal acceleration, and of course, is responsible for changing the direction, okay? Not the point, not changing the speed of a point, but changing the direction of the motion. So even if the speed still is constant, yeah, for acceleration, of course, a point moving in a circle path, it gotta continuously change the direction, yeah. And of course, that requires acceleration. So what it means is like if you think about this, and you're rotating that way, let's say, or the opposite direction, doesn't matter. In this example, we just want to rotate like that. So that direction, okay, changes like that. Okay, as you rotate over and over again, okay? And that's what we're talking, okay? And of course, we split the acceleration of a rotation, yeah, of that point into two. One is a tangential that changes speed, and the other one is a centripetal changing the direction. So you have a direction, and then of course you have a speed. If you look at the change in speed, we call that tangential. If you look at the direction, okay, direction changes of that, okay, a point right here, this point belongs to a little material of that rigid body. And we're talking about the centripetal, acceleration. Centripetal direction, tangential the magnitude, yeah, changes in the speed. What are we looking at? We're looking at the velocity over some time, yeah, to get the acceleration. So don't forget that as well. So in rotation, yeah, rotating a rotational motion, um, acceleration doesn't mean, all right, speed change. You have to understand that there is a change in direction, okay? So in rotation or rotating motion, tangential acceleration changes. Of course, it's showing you how fast the object rotates. And of course, while normal acceleration, that is your centripetal acceleration, is going to keep that motion, all right, going in a curve like that, meaning the direction, changes is accounted for in this study of the centripetal acceleration. We're studying the acceleration direction and of course the amount or the magnitude of that, which is the speed, changes in the speed. All right, so now let's get into tangential acceleration, the very first part of the acceleration in rotation. So tangential acceleration is actually the part of the acceleration, and we are not looking only at the change in speed, all right, during that rotation. So tangential acceleration, it happens only when your angular speed is changing. Okay, so if your angular speed is not changing, you don't have the tangential acceleration. And don't get confused with the linear speed. Okay, you have a two speed going on. Now we're looking at the angular speed about, okay, about this motion. So angular speed, if that changes, you're gonna have a tangential acceleration. Okay, so if the angular acceleration, which is your offer, this is your angular acceleration, is not zero, meaning there is angular acceleration. Every time the problem said there's no angular acceleration, okay, it's not, you have to understand it means zero. No angular acceleration means zero. If the problem say like the angular acceleration is completely zero, okay, and if the problem say it is not completely zero, you have to understand you need to relate that to motion, okay? So angular acceleration is not zero. It means that your tangential acceleration is, okay, there with the motion, period. So the relationship between this tangential, okay, acceleration and the angular acceleration um, is usually given by we write it this way. Yeah. So A, of course, your sub T is going to equal to R times the alpha. Yeah. So pay attention which one is a angular and then which one is a regular one. Yeah. So your regular one is going to be this. Okay, which is your just regular A, and then of course the sub is T, and then of course this is your offer, yeah. Your offer is your angular, yeah. So this is your angular um acceleration. So don't forget this is your angular acceleration. This is your tangential acceleration. And we call the tangential acceleration regular acceleration. So therefore we use a regular A, okay? Um, Angular is in rotation, yeah, acceleration for the rotation, and that we call it offer. Do not confuse between the two, okay? This is your tangential, and that is your angular. Every time there is a linear tangential, is always gauged with your R, okay, how far away. So this is going to tell you the points farther from the center of the rotation. Again, we gauge with R. R is always measured away from the center of the okay, axis. So the center of the rotation experience you're gonna have larger R, okay? So far away from the center, so larger R. So the rotation is gonna this thing, your rigid body is gonna experience a larger tangential acceleration because of this formula. This one go up, this one will definitely go up. Yeah, it's your algebra. So tangential acceleration is going x along the tangent to the circular path. So I already draw that for you, okay? Again and again, the same thing. So here is your circle. We usually draw like that. And of course, this is a tangent point. Of course, this is, let's say, like away from the axis, okay? This R little point, which is this, the distance we're looking at, okay? Not the point, the distance we're looking at. So every time we write the R, it should be actually here, and you will see, most of us right there, even though we draw the point. So don't confuse with the point. Point, usually we give the little symbol P, okay? So anyways, R mean like the distance is from here to here. I like to write it this way, and then of course I put a little mark like that, and I'm looking at the distance, so I know. And of course your tangential acceleration, okay? Is going to act along that tangent to the circular path. Yeah, so your A is going to be somewhere going on here. Yeah, so of course, in the direction of that motion, if the object is speeding up, let's say like it's going that way, okay, it's doing like this, so it's gonna go that way, okay? So that's your tangential acceleration. So in the direction of the motion, if that object is speeding up, it needs to be speeding up in order for this to be here, yeah? For the tangential acceleration to happen, you have a specific angular acceleration and your rigid body is speeding up, yeah, even though we're looking at that distance, of course, a point on the rigid body. So in the direction of motion, if that object is speeding up, and of course, in opposite the direction of the motion, if that object is slowing down. If that object is slowing down, your A is going to be going this way, but the motion is still this, but it is slowing down. Okay? Motion direction and acceleration directions are two different things. You might be going forward, but it might be slowing down. At that time, your A reverse, okay? Your A reverses, your tangential acceleration reverses. Motion is going on, speeding up, A is with it, okay? Your tangential acceleration is with it. Okay, so if angular acceleration is zero, yeah, your angular offer, if offer is zero, okay, then your tangential acceleration is also zero because it is equal, see, to if this is zero with algebra, when zero is multiplied with a number, it will be zero. So therefore, your tangential acceleration is also zero, yeah, even though the object may still be rotating. All right, now we are going to study the normal or the centripetal acceleration. So let's take a look at it. We call it normal, and it is because it's pretty normal, okay? And of course, another term is the centripetal acceleration. So let's see what is this normal about. So normal acceleration is the part of the acceleration that is definitely responsible for changing the direction of motion, okay? Not the speed, but changing the direction of motion. So in circular motion, normal acceleration always points toward the center of the circular path. So let's draw that. So here you have a circular path, all right, like that. So this is a circular motion, rotation, of course, drawing a 2D and a normal acceleration. We usually put a little n, tangential for t, okay, little t, of course. So normal, okay, your circular motion, normal acceleration, always gonna point toward the center of that circular path, okay? So something like this. So the magnitude of that normal acceleration, we're going to calculate this way. We're going to use, right, square of v. So v squared divided by your distance. So your distance again is a point of this. I usually write like this for the distance from the center to there, a little r like that. Of course, some people might like to write right here, but it's kind of like crowded here. Of course, your normal acceleration is going to point towards the center as well. Yeah, so it's very, very important that you know the normal acceleration exists when, even when the speed is going to be constant, meaning like this speed is constant. If constant speed, it will be, of course, two times of that immediately, yeah, after these are historic. We have already experiment measure and then deduce a formula and formula end up like that. Yeah, so your normal acceleration has an amount two times of that velocity. Yeah, two times of the velocity. So velocity times velocity. This is a linear velocity, by the way. Yeah. And of course, divided by that distance. Yeah, how far away the point of interest of us. Yeah. Um, this is, I don't know why a student out of all the equation, they usually forget that. So make sure that the normal acceleration depends, yeah, depends on the linear speed, which is this guy. So normal acceleration exists when the speed is constant. Yeah, even when the speed is constant. So even if an object is moving at a constant speed, it must continually change direction. Okay, to of course because that's going this way, so it will continually change the direction to stay in that circular path. The direction gotta change for it to be able to stay in a circular path, yeah, for the object or the rigid body. And of course, that change in direction gonna requires your acceleration speeding up. Otherwise, it won't roll. Yeah, it need to speed up to maintain that, by the way. So that's why your constant speed, okay, does not mean zero acceleration in circular or rotational motion. Yeah, normal acceleration exists because the velocity vector is your velocity vector is a constantly changing direction as your rigid body moves around that circle. Okay. So what you have just learned is we're not when your velocity, okay, for acceleration to happen, you're not looking at only the magnitude of the speed, okay? That is the key point of it. You have to consider the direction of that thing as well, okay? Direction of your rigid body as well. So acceleration is a vector and we consider direction, okay? It is a mandatory consideration, mandatory, okay? You will have to you will have to understand your acceleration depends on the speed, magnitude, and the direction of that rigid body. So now your object in this case is moving at a constant speed, whatever. Yeah, even if it is moving at a constant speed or with a speed, it got to continually change the direction. So acceleration, we're looking at the change in the velocity. So the velocity, the change in velocity doesn't mean it's only change of value, but the velocity can stay constant, but as soon as the direction change, you also get the change in acceleration. Okay, you have the acceleration. So of course, the magnitude will stay the same, but there is a direction vector is there. Yeah, the vector of the direction is there. So the direction changes in a circular movement. Yeah, and we are looking at a constant speed situation, but we know that there is a continual change in direction because your body, rigid body, is staying in a circular path of rotation. Okay, so that changes the direction. Of course, as soon as that happens, you have the acceleration. Yeah, and of course, now we're concentrating on the centripetal acceleration depends on that change, okay, in direction on that circular path. So that's why constant speed doesn't really mean, again, it doesn't mean zero acceleration, yeah, especially in this situation where circular or rotation motion is going on. So normal acceleration always exists because the velocity vector is constantly changing direction as the object moves around the circle. So if the object moves around the circle, we have a constant change in direction. If we have a constant change in direction, you got the normal acceleration, also known as centripetal, okay, acceleration. All right, now we are going to go back to our rotating, fan blade again, to be able to truly understand, okay, what's going on in this rotation. So here we're going to put some values, all right, for our variables. So your radius is going to be 0.3, yeah, meters. So R is your radius because radius is the distance, of a point away from the axis, which is your center, rotating axis. So that's a 0.3, and in your head is R, okay? Of course, your angular speed, which is your omega, which is this guy, is 100. All right, radian per second, because we measure the angular speed in terms of radian. Yeah, so 120 radians per second. Of course, we calculate that and we will immediately get the linear speed. Yeah, so this is how we get the linear speed. So that's a 36, of course, meter per, of course, second, because radian just gone away. Yeah, so meter per second is going to be your velocity. So the fan, has the angular speed is 120 radians per second. So we can now be able to calculate the linear speed of the tip of the blade, at that point 0.3 meters away from the axis. So since this is a rotating object, we want the linear speed of a point, at a distance from the center, and we use this equation, which is V is equal to R times omega, radius 0.3, omega 120, calculate, you're going to end up getting, 36 meters per second. So make sure you know that the unit work out cleanly, don't try to look for the radian, it disappear, okay? You don't put meter radian per second. Radian is just gone. All right. Traditionally, we write this way without writing the radian at the end, okay, of your linear speed unit, because linear speed velocity is meter per second. Yeah. There's no radian in it. So the tip of that blade moves much faster, of course, than the points closer to the center. Yeah. Because as you go towards the center, at one point there won't be any zero radius, So at the center point is going to be this is going to be completely zero. That's why your linear speed is completely zero as well, And if you think about the omega, we can do the algebra by taking this on that side, it would be undefined, for omega, you don't know at that point. So it's kind of weird. So this example shows you how your angular, of course, a motion, gives you the linear motion at different locations, on a rotating body. Of course, the different locations are measured by the radius. Okay. Let's take a look at example 2. So our example rolling wheel. All right, so here, let's see what the problem is giving us. So we got radius 0.5 meters, and then we got angular speed is 10, all right, radians per second. And of course, your problem is saying the wheel rolls without slipping. The rolls without slipping is your major, point. So it means like it is rolling without slipping. Mean there is a direct relationship between the wheel's rotation and its forward, okay, motion. So we are gonna put all of that together and come up with this equation, which is your linear, speed is equal to your radius times your angular speed. Okay. Throw in, plug in all of the units and the value 0.5 meters, 10 radians per second. Calculate. Yeah, so it's going to give you 5 meter per second. Okay, meters per second. Radian is going to be gone away again here. Yeah. So this problem is just teaching you, how rolling motion example. So this rolling motion mean a rigid body is in rolling. Okay, the motion type is rolling. So when you think about rolling, it is going forward and also rotating. So you got translation and you got rotation at the same time. So that's your general plane motion. And of course, how the no slipping, no slipping condition directly links to that too, which is rotation and of course translation. if rotation and translations are happening at the same time, you wouldn't get slipping. Okay, you won't slip at all. And that's what most of the sports, right? They use this technique to be able to slide, yeah, and of course spin, roll around, and also translate at the same time. Yeah, your figure skating, yeah. Yeah, if you watch the Olympics, right, they're going with their own like speed like that, and at the same time in totally control of that motion, yeah, without slipping, is because they're incredibly good at managing this general plane motion. Yeah, rotation and translation they're trying to do at the same times. Okay, so whenever you see, yeah, the phrase rolls without slipping is a very powerful, yeah, phrase for you. So you should understand that your linear velocity is going to be the distance, yeah, uh, the distance, of your particle or the point in that body away from the rotation axis, all right, times your angular, velocity. Okay. All right, so let's wrap this up a little bit. So before we wrap this up, this chapter, we're gonna look at the common mistakes that you can do when you study the rigid body. So the very first one is mixing the degrees and radians. I told you several times, yeah, it's just radians, no degrees. So using degrees instead of radians in the formula, like your V equal to R omega, is going to give you the wrong answer, so don't do that. Yeah. The second one is forgetting about the radius. Your radius always affect the linear speed, okay, because they are related to each other. Your linear velocity is equal to, okay, or linear speed is equal to the radius time your angular speed, okay? Now there's a common word issue. Yeah, they usually say and write speed and velocity as speed. Okay, you just look for the direction, by the way. So don't wonder about is speed the velocity, is speed just a speed. It depends on the problem, but they everybody loves to talk the velocity as speed. Okay, but velocity is the speed with the direction. So all you have to do is just try to find and don't take it by word. Okay, if you take it by word, you're gonna go crazy. When we say linear speed, we're talking actually about the velocity. Okay. So that just English, yeah, English word is kind of confusing. So anyway, so the second mistake again, don't forget, yeah, forgetting that radius affects the linear speed. So do not forget, radius is gonna affect your linear speed. It depends on it. Your linear speed depends on how far away, yeah, your point is, your point of interest, point of study is away from the axis. Yeah, so therefore the bigger that radius is, the faster your speed is linear speed, okay? We have two different speeds. All right, so even though your angular speed is the same for the whole body, of course, points farther away from the center move faster, than the points closer to the center. You have to get this. The third mistake, okay, the third mistake is assuming your speed, okay, must change for acceleration, to exist. So so in every circular motion, your object can move at a constant speed but you still have acceleration because again, we link it back to normal acceleration, centripetal acceleration because there is a change in the direction. So directional motion is always changing in a circular path. So therefore, even though your magnitude is the same, constant speed, you still have the direction, change in direction. So you have the acceleration. Okay. So the final mistake is so do not, of course, the third one is do not assume speed change is required for the acceleration. No, you don't need the speed change for acceleration to exist. Okay, if there is a direction changes, you have acceleration. And the last one is uh, sometimes you don't identify the motion type, first. Make sure you always identify the motion type. So make sure you always decide whether the motion is translation, whether it is rotation, or whether that's both, general plane motion before understanding your situation or before, let's say at school, before, choosing your equation. on the book. Of course, at school is on the book, but at work is you have to deal with different machines, yeah, and a different issue and problems, repairs, of course, means depends on the speed, yeah, the distance, and what's rotating. All right, so yeah, that's all the mistake that you have to be careful, yeah. Okay, your in-class practice are listed there for you, just a general. You can just go to your textbook and then do the problem. Your gear rotation, rolling, yeah, motion, because identifying the motion type is really important before solving the problem. Always you also need to include your units. Yeah, don't forget, do not make mistake in your units. And of course, the student works. I write it down here. Make sure your rotation problems, rolling motion problem. Make sure you show steps, and then include. All right, a unit. So this is kind of like I made a mistake here. I might wanna yes, a delete. Okay, one of this. Probably I duplicated yeah, so far. Okay, lesson summary is going to be rigid body is gonna move yeah by translation, and then of course the rotation or both. Yeah, so that's your general plane of motion. Of course, your angular and linear motions are connected. Don't forget that. Your rotation, all right, creates a different speeds at different radius. Don't forget that different radii, of course, in plural. And of course, this lesson is going to set up future, yeah, kinetics topics. We will relate kinematics to kinetics. If you know kinematics, is really easy to figure out what course, yeah, that motion. Okay, so today we finished the motion, yeah, stuff, and then of course we don't study the forces because we're still in kinematics. Motion first, and then your causes is going to be second to study. And here is the source I identify here, yeah. All right, that's it for chapter 3.